Hello, ladies and gentlemen. Here is Tong Chao, come from Beihang University. Today I'm going to introduce my work, GNNavigator. It's a framework for adaptive GN training. GNNavigator can achieve convenience results under many scenarios. So let's start with the basics. What is graph and what is the GN? Nowadays, graphs are everywhere, from social networks, molecular structures, to transportation networks. They're typically equipped with node features, edge features, and graph topology. GN are a type of neural network designed to work directly with graph structures. It can be classified into two main stages: message passing and activation updating. Message passing is where each node in the graph sends information or messages to its neighboring nodes. During the activation updating stage, once a node has received messages from its neighbors, it processes these messages to update its own stage and activation. Thanks to the well-sound performance of the latest GPU and FPGA, GNN typically runs on heterogeneous platforms for training efficiency. It means they use a combination of different types of hardware to get the job done. Complex operations such as sampling and file RO are mainly executed on general-purpose platforms we call host. Massive but simple operations such as aggregate and combine are conducted on dedicated designed platforms, which we call device. By doing this, GN training becomes more flexible and parallelizable. In the diagram, you can see we have topology data, which shows how the nodes are connected, and feature data, which contains information about each node. On the right, we see the GN layer in action. First, there is a message passing, which node exchange information. Then comes activation updating, where each node updates its state based on the messages it received. And that is the basic idea of how GN works. It is all about efficiently handling and processing complex data structures using the power of graphs. Now let's dive into the various optimizations that exist for GN. When we talk about optimizing GN, we are typically focusing on several specific performance metrics. For example, time cost or memory usage. Some methods are specifically designed to reduce the time cost. Pure graph designs, static cache policy. BGL employs dynamic cache and enhances the system's throughput. GNAdvisor provides guidelines for optimizing GN execution on GPU. There are 2P graph and many other works focusing on time cost. On the other hand, some works focusing on reducing memory consumption. Efficient memory usage means we can handle big graphs and more complex data without running into hardware limitations. Exact EXACT designs compression methods. ADAQP and VQGN take quantization techniques to control the runtime memory consumption. So depending on the specific needs of your GN application, you might focusing on some specific metrics such as time cost, memory consumption, or even some others. Yes, you might considering one or several of these metrics. This imposes an adaptive requirements on performance metrics according to different applications. Continuing with our discussion on GN optimizations, let's explore another important aspect, the compatibility of different optimization techniques. Previous researchers have introduced many optimization techniques. Can we just combine them and expect a better performance? For instance, consider activation, compression, and GPU-oriented operator optimization. Both are crucial, but combining them seamlessly is not always straightforward. Activation compression reduces the memory consumption of activation data. On the other hand, GPU-oriented operator optimization aims to maximize the throughput and efficiency of GN computation on GPU. This helps in speeding up the computation, making the process much faster. The big question is, can we achieve both memory efficiency and high throughput simultaneously? Unfortunately, in most cases, the answer is no. Achieving compatibility between different optimization techniques can be tough. In summary, existing optimizations mainly face two challenges: how to be adaptive, and how to be compatible. For the convenience of next research, we generally abstract different optimization strategies as sampling optimizations, transmission optimizations, computation optimizations, and framework optimizations. About sampling optimizations, they are node-wise, layer-wise, and subgraph-wise sampling. Furthermore, for the latest research spotlights that locality-well sampling can achieve relative better performance. Yes, we will consider it for our GNNavigator. Yes. When it comes to transmission optimizations, data prefetching can be widely used in various optimization frameworks. Some researchers investigated the device cache management to fully utilize device resources. Others have developed activation compression techniques that significantly reduce the overall data transmission requirements. About computation, there are parallel computation optimizations which take the divide and conquer and some other parallel methods. For instance, works like fusion design, GN-oriented operators, greatly enhancing the performance of GN on GPU. Finally, there are framework optimizations to explore the pipeline optimization such as Science. They consider the training process as a whole, and they optimize the training from a higher view. Yes, here is existing GN optimizations, just a list or categorize. Yes. Considering all the things mentioned above, we can conclude three key challenges on GN training. Firstly, we have the challenge of compatibility. When you are trying to integrate many different algorithms or techniques, it is crucial that they work harmoniously together. The aim here is to achieve performance enhancement, while the whole is greater than the sum of its parts. Imagine combining two powerful algorithms and getting even better results than you would expect. expect from either of them or not. Next up is adaptability, as can be seen in the right diagram. In the real-world applications, different scenarios demand different performance metrics. Well, whether it is accuracy, time cost, or something else entirely, we need our GNN to be flexible enough to adapt to these varying requirements. This challenge is all about making sure our models can handle a wide range of situations effectively. Lastly, we come to automation. We would want our GNN to run smoothly without constant human intervention. This challenge is about reducing the need for human laboratory, whether maintaining or even improving performance. According to the given application requirements, we expect a training framework that can automatically adjust its configuration and combine an adequate techniques to achieve a promising performance. These are the three challenges: compatibility, adaptability, and automation. To solve the three challenges, we introduce GNNavigator, an adaptive GNN training configuration optimization framework. GNNavigator automatically generates training guidelines, consistently delivering promising performance across different scenarios. First, users need to handle the initial data and configuration settings that are fed into GNNavigator. This data may include graph structures, node features, edge features, and any other relevant information required for GNN training. GNNavigator takes the input data and performs several key steps to optimize the GNN training. These steps include: first, the pre-processing. The framework first analyzes the application requirements and marks the performance metrics that should be highlighted. Then it profiles GNN models and datasets to obtain their characteristics. And step 2 is the guideline generation. In step 2, GNNavigator automatically generates GNN training guidelines, taking both export targets and runtime constraints into account to ensure its adaptability. We further design gray box performance estimator to accurately predict the training performance with relatively low overhead. Finally, we come to training. Users receive the guidelines in the form of training configuration settings and apply these settings on the GNNavigator's runtime backend of GNN training. Finally, we get the output. GNNavigator guarantees that the actual training performance not only satisfies application requirements but also outperforms other handcrafted designs. In summary, GNNavigator provides a comprehensive framework for optimizing training and configuration of GNN, leveraging both data-driven and runtime adaptive techniques to maximize model performance. The main design logic of GNNavigator is shown in this slide. First, we construct a unified GNN backend with a general abstraction of many existing optimizations, and we support many GNN models and hardware platforms. The backend builds an overall abstraction of GNN training from algorithms to hardware. Upon the backend, we learn a gray box model to estimate GNN training performance under given configuration. The gray box model is trained offline with tremendous training cases. The model will help us make precise and efficient performance estimation without actually training the GNN model, which is time-consuming. training optimization is work on the two above parts. It explores the design space with the help of performance estimator and deploys the training tasks on the unified backend. By constructing the performance Pareto frontier, we can guarantee a promising training setting as a guideline. The first thing we have to ensure is that our backend will not perform worse than existing works. We ensure this by designing a highly reconfigurable unified backend. Thanks to its reconfigurability, the runtime backend can represent itself with diversity performance, making it adaptive to a wide range of applications. Furthermore, we make some configuration setting templates to produce many previous works. For instance, by disabling cache update policies and properly configuring the cache ratio, the backend generally reproduces the approach proposed in peer graph. Above the backend, we can not only combine different optimization strategies flexibly, but also fine-tune configuration settings for better performance. When it comes to scalability, the backend is established upon the categorization and abstraction of existing optimizations. Only if the method satisfies our abstraction, we can incrementally support the further works. The key steps involved are as follows. For automatic guideline generation, first is the initial set. We begin by identifying the initial setting and templates that will serve as a start point for our exploration. By doing this, we will greatly reduce the exploration time and ensure the performance. All the configurable settings constitute the design space. Each point in the space can be called a candidate. Then we come for the design space explorer. Every time the explorer takes a candidate from design space, it passes the candidate to performance estimator, fetching back the estimated performance without actually training. Decision maker will decide whether the performance satisfying runtime constraints and whether the result outperforms others. Finally, we come to the Pareto front generation. We generate the Pareto front, which represents the optimal candidates based on the defined metrics and constraints. The process ensures that we identify solutions that balance multiple performance objectives while adhering to defined constraints such as a device memory or bandwidth or others. Some hardware constraints or limitations. Yes. Here we present the performance estimator with its important gray box model. The estimator predicts GNN training performance in a gray box manner, combining purely theoretical analysis, which is called white box, and machine learning methods, which is called black box together. To ensure the accuracy of estimation, the estimator first theoretically analyzes the data dependence between its inputs and performance, which we consider as the white box. Considering the complexity and the randomness of graph, black box model based on machine learning are introduced to estimate some key intermediate variables or functions that influence performance. For instance, we define the sampled subgraph of each batch as Vi, as can be seen in the formula. It shows many times, so the Vi is very important. The Vi is the mini batch size. Yes. So we view it as a key value, and the formula of minibatch size can be presented as this, as we can see in the slide. The f overlapping is the so-called learnable function, indicating the overlapping among different minibatches. However, the overlapping is hard to generate a precious function, so we take a black box model to estimate it. Here we can see the effect of estimation. Yes, we can see the gray box model greatly outperforms the black box model. Yes, it is very good. We evaluate GNNavigator on various GN training tasks. We preset several application requirements and explore the design space thoroughly for optimal performance. The chart shows the performance metrics such as time, memory consumption, and accuracy for different datasets and methods. GNNavigator generally achieves similar or superior performance compared to baselines across various GN training tasks denoted as balance. GNNavigator can further improve training performance in certain metrics with a marginal trade-off in others, which is marked as extreme in table. As you can see in the chart, in stage model training on OGBN products datasets, our balance mode achieved 2.5 times acceleration, 7.5% reduction in memory, and slightly accuracy enhancement at the same time. And if we sacrifice a bit of accuracy, which means extreme mode on time and memory, the acceleration can achieve up to 3.1 times. In this way, we can adaptively provide GN training guidelines for users to achieve promising performance under different scenarios.